So yesterday's lesson was all about the sets of three. Okay? So we had the three fates of light. What were the three fates of light? Light strikes the Earth's surface to be absorbed, reflected, or converted by photosynthesis. Okay, so we got to know those things for sure. How much of each happens is affected by what? Starts with A. Albedo, right, the reflectivity of the Earth's surface. Okay, good. We talked about the three parts of the Earth, the atmosphere, the hydrosphere, the lithosphere. Lithosphere doesn't do much other than provide soil for plants to live in, and they obviously convert the solar energy. Also, it influences the albedo. Okay, in terms of the hydrosphere, obviously there's ocean currents and things like that for transferring energy, but its biggest role is part of the water cycle, which is where it interacts with the atmosphere, in that thing we call latent heat, right? All that energy that gets carried in water vapor from one place to another. That is going to tie into today, okay? Today we're going to be talking about latent heat. We're going to be talking about one of the three methods of heat transfer, which was the biggest one. There was conduction, convection, and radiation. We're going to be talking about convection. Convection is the heat transfer method that works on a global scale. It is hot air rises, cool air descends. It is that cycling and movement of air. That's what we're going to look at today because we're talking about wind patterns, and how energy and wind and all of that kind of work together to transfer energy from warm parts of the Earth, that would be by the equator, to more northerly or southerly parts of the world. Right, so we're going to be looking at those wind patterns. There's going to be some key concepts in here, that you'll need to remember the names of and understand how they work. Okay, so first key point, understand how energy is distributed on Earth. We kind of already looked at that. That goes back to the number one factor affecting climate, which is latitude. Okay, the number one factor affecting climate is latitude. That means that near the equator, they get lots of energy. Near the poles, they get much, much less. Okay. Understand the role winds play in distributing that energy. So we're going to look at patterns of prevailing winds. We're going to look at wind systems. And we're going to look at the jet stream as well. We're also going to talk about the Coriolis effect. The Coriolis effect is a deflection of winds, because winds are just moving north and south. They're moving that way because of the differences in temperature. Right? Hot air rises, cool air moves into a place that the hot air goes north. But while all that is happening, the Earth is spinning underneath it. The air, the Earth's atmosphere, and the solid part of the Earth don't rotate together when the Earth spins. The atmosphere is not connected to the Earth completely. So the Earth spins underneath its atmosphere while the atmosphere is doing its thing, and there's this dragging effect of that makes winds that are supposed to be going north and south actually deflect east and west because of the rotation of the Earth. That's the Coriolis effect. I'll demonstrate that with a volleyball when we get to that point. And recognize that global wind patterns are a product of convection. Convection is that number one single largest method of heat transfer when we're talking about weather, climate, and energy transfer on a global scale. So global wind patterns, which is what we're looking at today. Why does wind here always come from the southwest? We're going to be looking at why that is. That is convection and the Earth's rotation. That goes back to this. The Coriolis effect. All right, questions there so far? Okay, what does the second law of thermodynamics say?
Heat flows from hot to cold.
Exactly, heat flows from hot to cold. That's why convection happens. Energy always wants to flow from high to low, hot to cold in this case, because we're talking thermal energy. So we're going to be looking at how that works. And what the Earth's rotation has on that. Okay, so here's what goes on. The Earth spins this way. So the gray arrow here is showing that the Earth rotates this way. That's why the sun rises in the east and sets in the west. Just a few hours ago, like at about 4:15 a.m., we would have been on the other side. So we would have been in the darkness. So right about here. Now, as the Earth spun, it appeared as though we came into the light. So if we looked to the east, we would have seen the sun coming up. Obviously, it's not the sun going over the Earth, it's the Earth spinning under the sun. Okay, so over the course of the day, we move over to here, okay? The sun stays where it is, but from our perspective, it looks like the sun is going to be setting in the west because we're going to turn and go onto the dark side. Okay, everybody with me there? Now, when air is trying to go up or down, as the Earth spins under it, it appears to get deflected. Okay, it's kind of like this. If I go outside right now, there's no wind. If I stand outside, I feel virtually no air movement. Okay, but if I get in a car and stick my head out the window, not a good idea by the way, but okay, if I do that, does it feel windy? Okay, it's not because it is windy, it's because I'm moving through the air at a high rate of speed. That's why winds feel like they're coming from one direction. The Earth is spinning and throwing you through the air, okay, as it rotates. Okay, so some of the winds we experience are not actually coming from the direction we think they are. They just feel that way because we're moving into them as they go. All right, everybody with me there? Okay, so by the way, this only, again, works if that whole Earth is round thing. Okay, because the Earth's round. Okay. Okay, so this is relating to the second law of thermodynamics, right? Nature does not like imbalance. That's why the second law of thermodynamics exists. If one area is hot, another area is cold, energy is going to flow in the direction of hot to cold. Okay? The same is also true with pressure. If there's an area that has high pressure and an area that has low pressure, okay, then it's going to equalize. It's going to go from high pressure to low pressure. Okay? And that's what can cause rapid changes in weather. Okay? We experience that here all the time in Alberta. Okay? It's why we have the saying, if you don't like the weather, wait 5 minutes. Okay? Right? You guys heard that, right? Because that's how quickly things change here. Okay? And that has to do with locations of high and low pressure. Okay? Being close to the mountains can actually create areas of high pressure, and that can cause winds like Chinooks that we looked at the other day. Okay? So we sense the movement of air trying to balance inequity as wind. Okay, so in super important wind mechanism is the jet stream. Okay? The jet stream is the thing that meteorologists are always watching. Okay? It is a high altitude, high speed wind mechanism. Okay? We call it the jet stream because jets can fly in it. Okay? But you only want to be in it if it's going the right way, or you're going the right way. Okay? Otherwise, you want to avoid it. Right? So most of the time, okay, the jet stream looks like this, and it goes across North America. There's also one in the southern hemisphere. Okay? It goes across North America kind of like this, and its shape changes depending on pressure. Okay? If there's an area of high pressure, the jet stream will bend around it. If there's an area of low pressure, the jet stream will bend around it. Okay? And so its position and shape changes all the time. Most of the time, okay, it's just kind of like this. It kind of just goes across. Okay? The northern hemisphere is a little bit wavy. Okay? And that's really about it. Pilots want to know its location. If they're flying this direction, they'd like to get up into the jet stream and get a little boost. Okay? It allows them to fly a little faster, use a little less fuel. It's like having a big tailwind. Okay? How many of you have ever been on a plane and you hit turbulence? Okay? Kind of scary, right? If you hit a lot of turbulence, it usually means you're crossing the jet stream. And one of the things the pilots will do is either, well, they'll change their altitude. They'll either go up or down to get out of it. But when you're crossing it, that's going to make for a rough flight. That's when the fasten seatbelt sign will come on and it won't be bringing the drinks around anymore. Okay? Because it's just too dangerous. Everybody needs to be seated. Okay? If you hit a pocket within that jet stream of cold air, the plane can fall very rapidly. Okay? That's why they tell you to always have your seatbelt on when you're seated. Okay? Because there have been cases where people have taken their seatbelts off, the plane hits a cold air pocket in the jet stream and just falls, okay, like several meters. Well, if you're standing in the aisle or you're sitting in your chair without a seatbelt on, okay, the plane rapidly falls, you stay put. Okay? And so the plane falls and you get thrown into the ceiling. Okay? There have been cases where people have been killed by having their necks broken. Okay, from hitting their head on the ceiling and it snapped, like flight attendants and stuff who were not belted in when they suddenly hit one of these pockets. Okay, so that's why they always tell you, if you're seated, have your seatbelt on. Okay, just in case you hit one of these, but that's usually related to the location of the jet stream. Okay, now the jet stream's main role, okay, is to move the latent heat that we were talking about yesterday. Okay, the latent heat that is part of the water cycle. Right, so the jet stream, okay, and you will want to add this. Okay, this is the main job of the jet stream in terms of energy transfer. Okay, the jet stream is important for moving latent heat. Okay, because of its nature, it can push air masses around. Okay, and that's why it can cause rapid changes in weather. If the jet stream radically changes shape, as it does that, it pushes the air below it out of the way. If that's got a lot of moisture in it, it's pushing all that moisture, that latent heat, somewhere else, and then that represents a lot of stored energy. Okay? Everybody kind of with me there? So that's the main job of the jet stream. Make sure you make a note of that. That is something you would work into an answer. Okay? If on a test I asked you, how is energy transferred from the equator to more northerly parts of the world? Okay, obviously convection would be a big part of that. Okay, but the jet stream would also be a big part of that because it's what's going to move all the latent heat that's part of the water cycle from one place to another. Okay, so here's how the jet stream works. This is a really unusual shape for the jet stream. Okay, there was a high pressure area in a place that you usually don't see one on this particular day. Okay, so the jet stream had to get pushed up to the north around that high pressure area. And when that happened, it pulled a bunch of northerly cold air and pulled it and forced it southward. Okay, now this happened on a summer day. Okay, so this would have happened like in July. Okay, and you can see then that all of the prairies would have been in kind of a cold front. Okay, we would have had cooler than normal temperatures. It would have been summer, but it would have been like 17 or 18 degrees when it should have been mid-20s. Okay, now the problem with this is the jet stream got forced back out over the ocean where it would pick up a lot of what? Yeah, water, a lot of moisture, right? There's a lot of moisture-laden air over the ocean. So when it got forced out over here and then pulled back over, it pulled with it a whole bunch of moisture. So it's bringing cold air down here and then moving in moist air here. Well, when those two things combine, you've got cold and then you've got wet. Okay? You're going to get right through here, okay, in this green area, highly unsettled conditions. What is that part of the United States nickname? That would be Ohio, Kansas, Oklahoma. Ever watch Twister? That is Tornado Alley. Okay? That's where, Dorothy lived. Okay? They get all kinds of tornadoes, thunderstorms, things like that. And it's usually because the jet stream is moving across there. Okay? If there's an influence of cold air coming in from above, that's going to create a whole bunch of unsettled conditions that are ripe for building thunderstorms. This is an unusual shape. Okay? Most of the time, the jet stream kind of goes like this. Okay? Across North America, which means it's usually doing this and kind of this in the same area in Alberta. We're the Tornado Alley of Canada. Okay? We get more hail and thunderstorms than anywhere else in the country. Okay? In fact, insurance companies hate insuring for hail in this area. You have to pay extra to get hail insurance because they'll almost definitely have to pay out at some point. I mean, how many times a year do we get hail of significant size? 2, 3 times? That doesn't seem like much, but it is. From an insurance standpoint, that's a lot. Okay? You wouldn't see in, let's say, Quebec, that being a problem. Okay? They don't get hail like that. Okay. All right, so jet stream can push air masses around, and when it's pushing air masses around, it can change the weather rapidly. Okay? So because of its shape, it's usually moving back and forth across Alberta. Okay? And that's going to move air masses in different directions, which is why our weather is typically harder to predict. Okay? Making sense? All right, so make sure you have that stuff there about the jet stream, okay? Because that's super important in terms of moving energy from one place to another. Okay, so this is what our global wind patterns look like, okay? And they are an interaction of convection as well as the Earth spinning, okay? So obviously near the equator where they get the most energy, okay, that's going to be the hottest. So air near the equator gets hot and it rises, okay, and it moves up. Now, if air just moved up and nothing came in to replace it, you'd create a vacuum, okay? Obviously that can't happen. So when that hot air rises, air from further north moves in to replace it, okay? Each one of these little kind of cyclic patterns are a convection current, okay? So all of those circles represent convection currents. Okay? They're given different names that you don't need to know. I will never ask you about Hadley, Ferrel, or polar cells. Okay? I'll never ask you those names. They're just convection currents in different places. Okay? So you got hot air rises, air moves in to replace it. Okay? So that air then can't fall back down in the same place, so it gets pushed to the north. Okay? Now it's showing it as cold here, but by the time it gets to here, it's warmer than the air that was there, but it's descending. Okay? As it descends, it also meets other cold air that's coming in, and what ends up happening is that warm air gets pushed along the surface, okay? Because there's cold, dense air above it, right? This is the section that we're in. This is the section of the Earth that we live in right here, okay? And you can see the arrows show that the winds in this section typically get deflected from southwest to northeast. Is that typically the direction the winds come from here? Right? That's the direction wind comes from. That's southwest. Okay? Typically our prevailing winds are from the southwest. Now we are at the northern end of that band, okay? Which also leads to a lot of unpredictability in our weather. Now near the equator, the opposite is happening. Okay? Here, hot air is moving northward. Here, it's moving southward. So as the Earth rotates, it makes it feel like the air is being deflected out of the north. Ooh, that's a terrible color to use. Out of the northeast. Okay? Near the equator, the winds are almost always easterly or northeasterly. Okay? And they're so predictable that we've given them a nickname. Okay? They are called the trade winds. Okay? The reason they're called that is because hundreds of years ago, in the era of sailing ships, these were used to bring goods from the old world to the new world. Okay, so from Europe over to the Americas. And they were 100% reliable in doing that because they always blew from the east to the west. Okay, so there would be trade routes set up around these winds. Okay, so over here would be Europe. Okay, and so ships would leave and they would sail down the coast of Europe, so they'd stop in places like Spain and stuff like that, pick up teas and spices and whatever else, okay? And then they would get down to these latitudes here, maybe stop in Morocco and pick up, some cool stuff, and then they would sail across the ocean to the Americas on these trade winds. And then when they got to here, okay, they'd go a little bit north and they would catch these westerlies, sail up the coast, do all their trading, pick up whatever they needed, and take it back to Europe using the westerlies. Okay? And these trade routes were very reliable because the winds always blew from that direction. Okay? Making some sense? Okay, so the reason this happens is because wind or air is trying to do this. It's trying to move vertically north and south. But as it does that, the Earth rotates this way, pushing us through it as it's trying to move north-south. Okay, so as I push through this air that's trying to do one thing, it feels like it's going from a different direction. Okay, that's the Coriolis effect. Okay, I'm just going to grab this ball. Okay, so it drew a curve exactly like what we saw here. Okay, even though the winds are only going north and south, the Earth spins under them while they do it, and if I'm standing on the Earth, I'm thrown into that wind, and it actually feels like it's coming from the northeast instead of from the north. Okay? Now, the same is true at our latitudes. The Earth is going this way, okay? Air is trying to go this way, and it curves the other direction. Okay, that's why we get it from the southwest. Okay. All right, so that is the Coriolis effect. So that's why wind doesn't just move north-south. Okay? All right. Being able to explain this is also going to be important on your exam. Okay? When we're talking about how energy is transferred on Earth, okay, we are talking about convection. We're talking about the effect of latitude. Okay? Hot air is going to rise, cool air is going to descend. We're going to get a cycle going, okay? And we're going to get the Earth rotating underneath that cycle. Okay? That's all going to result in air moving and transferring energy from high to low. Okay, from equator to poles. Along with that, okay, the monkey wrench that can get thrown into that system is the jet stream. Okay, and that's what makes weather harder to predict, is where the jet stream goes. And while the jet stream is moving, it's bringing all that stored latent heat, that stored energy in the water vapor. So if I ask you a question on the test, okay, about how energy is transferred from the equator to the poles, the things that need to be included in that answer are convection, the Coriolis effect, okay, it's deflecting those winds, the jet stream, latent heat, okay, and second law of thermodynamics. Okay, it would be a 5-mark question. 1, 2, 3, 4, 5. Don't just write down those 5 words. Okay, you have to explain them. Okay, you have to tell me how they go together. Okay. And if you remember at the start of this unit, I said this unit is kind of a hodgepodge of every unit we've gone over. Okay, you kind of seeing how now. Okay, we've talked about plants carrying out photosynthesis. We've talked about laws of thermodynamics. Okay, we've talked about chemical energy. Okay, all those things. It all just kind of ties together in this unit to show you how the Earth works as one big system. Yeah. Wilson lives to fight another day. You guys seen Castaway? Wilson! I didn't put a face or anything. Okay, anybody need that one anymore? All right. All right, so we got this Coriolis effect thing going on here. That's the Earth spinning, okay, this way, which of course it has to be round for that to work, okay? But the air is circulating like this, okay? We just got 3 different layers of convection currents. Okay, 3 different layers of convection currents going on, Earth spinning underneath them. That is going to move air, okay, in large amounts, bringing with it sensible heat, that's the kind we can feel, like temperature, okay, as well as latent heat, that stuff that's stored in the moisture. Okay, now I'm going to show you a couple of quick videos kind of on how this works. Okay, I also found one on climate that I'm going to show you today as well, just so you kind of see the models moving as opposed to a picture of it. All right, is that making some sense? All right, so I actually had a picture of that from before, okay, and you can see those bands, okay, there's the big red spot, okay, and you've got winds going opposite directions on either side of it. Okay, so we talked about the Coriolis effect, okay, that this was the actual path thing, the target, but you missed the target because the Earth rotates underneath it as it's falling, okay? If we're moving towards the equator, the deflection is this way, so easterly. Moving away from the equator, the deflection is westerly, that's where we're at, okay? And so we see that pushing around of those winds. Okay, just finished, awesome. Okay, let's have you guys just jot down some quick answers to those questions here before the bell goes. Okay, on Monday, we're gonna go over specific heat capacity and latent heat. Okay, we'll finish up latent heat on Tuesday, and then do biomes. And then we'll finish up biomes on Wednesday and do the unit exam review. Okay, I believe I posted the unit exam review. If I didn't, I will. I'll double check for today. So you can have a look at it over the weekend. Probably not gonna help too much because we still have a good third of the unit left to go, okay, next week. All right, so Monday, Tuesday, Wednesday are gonna be fast and furious.